Hello, my name is Jessica Merrill, and I worked with Michelle Bono, Carl Dornstouter, and Jake Kuhn on the DaVinci clock for our senior design project. Our sponsor was Dr. Dan Budney, the director of the freshman engineering program. Multiple previous mechanical engineering senior design teams worked to design a version of the DaVinci clock. The clock pictured here is the version that the last mechanical engineering team designed during the summer semester. The clock took about 14 hours to make, and the parts cost about $43. At the end of the semester, the mechanical engineering team left behind one operational prototype. Our sponsor wanted to recreate this clock in the coming spring semester so that he could give about 50 clocks as gifts to the people who helped out at the freshman engineering conference. In order to prepare for the mass production of the clocks, our group needed to create a number of deliverables. First of all, we needed to analyze the assembly process and improve its efficiency. We needed to create a standard process and create official documentation of this process. To ensure documentation was effective, we needed to validate the building process by using the documentation as the sole source of knowledge to build a number of clocks. Finally, we needed to calculate labor and cost estimates in order to determine the price of production of a DaVinci clock.
The methodology used by our group to best assess the problem presented in this project included creating multiple prototypes at different steps in the process. At first, this helped our group become more familiar with the clock and how to assemble it, but we soon became able to critique the production process and improve the transition from raw materials to product. We fabricated sub-assemblies that would be crucial to the success of our proposed facility layout and worker flow diagrams. These multiple builds also allowed our group to conduct time studies for forecasting the labor needs and associated costs. Our quantitative methods for this project included both a cost analysis and material usage report. The cost analysis took into consideration the price of all factors that impact the clock, including items such as purchased parts, materials, and labor or shop time. The material usage calculation determined how many clock parts can be generated from the size of material we have been using. Our assumptions for this project included that we had no limit to access of labor, that the machine shop will be available for mass production as no associated costs, and that the facility layout and space available is variable. Our analysis also included multiple variations of flowcharts such as the one showed here. These were created for both the fabrication and assembly portions of the clock. High-level flowcharts helped establish a general idea of how the processes interact, while the low-level flowcharts get into more specific detail about the steps that may not be seen on a high-level map.
As a part of our analysis, we created a Yamazumi board to help us perform a line balancing exercise. This is a visual tool to help identify bottlenecks and even out zone tasks. As you can see with this board, our tasks are organized into the zones shown before in the flowchart. This separation of tasks takes around 20 minutes per zone, evening out the tasks to be within the margin of error of each other. This current line balancing represents an even flow throughout the assembly line. Next is our analysis of our stock material. This diagram and others like it demonstrate the best way to cut a piece of stock material to optimize the number of parts produced from each piece without overproduction. From this, we thought it was important to consider the scrap rate. With our material usage calculation, the scrap rate for each piece was kept under the industry standard of 10%. We were able to use this material usage in predictive measures and cost calculations shown later.
As part of our many deliverables for this project, we created a material ordering sheet and station layout. The material ordering sheet uses the information we collected in our material usage analysis to help us determine how much stock material must be ordered to produce X number of clocks. The station layout provides details on how each subassembly area should be laid out, which parts can be found in that area, and which equipment will be required to both assemble the clock and keep you safe. Since we are creating the clock assembly process from scratch, our group documented the process thoroughly throughout the assembly. We created detailed SOPs for all machine processes and the assembly process. The SOPs provide both directions and pictures to help guide you through each process. BOMs provide a list of the materials required for assembly, and the purchased parts list tells you where to buy stock material at the cheapest available rate for each material. The assembly aids and instructional video serve as additional aids to the SOP and outline greater details on some of the more intricate pieces of the clock. In order to calculate the total cost of the clock, we started off by determining the total labor hours needed to make it. We recorded several times for each step of the machine and assembly processes. We took the average of those times in order to find the standard times for the entire process. Once we had the total labor for the clock, we multiplied it by the wage provided to us by our sponsor to determine a labor cost. We then determined the cost of the materials for one clock and found the total cost for each clock.
We found the total cost of the clock to be $80.53.